Hello cadets. Now let's continue with the next optical instrument, that is a telescope. First, telescope is that optical instrument that we use to see distant objects. The objects which are far away from us, we want to see their magnified view, magnified image, so we employ a telescope. Now, based on the application, the use, the telescopes are of two types, that is terrestrial telescopes and astronomical telescopes. So as the name indicates, astronomical telescopes are used for observing the stellar objects, the objects that are there in the sky. To see them, to view them, we use an astronomical telescope. To see the objects on Earth that are around us, we use a terrestrial telescope, like maybe a spotting scope, maybe a binocular. These basically are terrestrial telescopes. Now, depending on the arrangement used and the phenomena involved, the telescopes are differently classified into other two types as refracting telescopes and reflecting telescopes. So obviously, as the name indicates, in refracting telescope, the phenomena of refraction of light is employed to get the magnified image, whereas in case of reflecting telescope, the phenomena of reflection and then refraction is used to get a magnified final image. So refracting telescope, also called as dioptrics, the branch of physics or optics dealing with refracting telescopes is called dioptrics, and reflecting telescopes is called catadioptrics. Now, here in this video, we are going to study the details about astronomical refracting telescope. So, the telescope that is used to see stellar objects, objects in the sky, and it relies on the phenomena of refraction only. That is, it involves use of only lenses. No mirrors are used, only and only lenses are used. Now, in this case, the lens that lies towards the object side is called as the objective lens. So, this is your objective lens. In front of this lens, there lies the object. Of course, the object is at infinity, that is far, far away from this telescope. Then the observer sees or observes the final image through a smaller lens called as the eyepiece. It is called as the eyepiece. Now, the image formation for the objective lens is simple, is same for all cases. Object at infinity, image at the focus. So, whenever object is at infinity, then the lens receives parallel rays from that object. So, this object, these rays of light are coming from an object which is at infinity, and therefore after a refraction through this lens, these rays are going to converge at the focus of the objective lens. So here you are going to get first image. So object at infinity, image at focus. Now we know image at focus, this is going to be a real and inverted image. Now in front of this, there is a smaller mirror that works as an eyepiece. Now, first important point about such setup where multiple lenses are used and multiple images are formed. Okay, the first important thing is that the image formed by first lens, that is the objective, image formed by the objective will serve as an object for the second lens, that is the eyepiece. So in this setup, image formed by one lens, the first lens, will serve as an object for the second lens only and only if this is a real image. Okay? Image formed by first lens will serve as an object for the second lens only and only if it is a real image. So imagine that this lens is giving you a virtual image, then that's the end of it. No further image formation is possible no matter what kind of lens you are using here. It doesn't make a difference to a refracting telescope. Now, moving ahead, this ray diagram that we are seeing here is when this telescope is used in normal adjustment. So, normal adjustment is when the final image is formed at infinity. The final image is formed at infinity. So, for normal adjustment, final image is at infinity. So, image formation of objective, object at infinity, image at focus. Focus of the objective. That is why this point here is the focus of the objective. Further, distance here will be equal to focal length of the objective, that is, it will be denoted by FO. O stands for objective. Now, for a moment, forget the objective lens, just for a moment. You have this object placed in front of the second lens, that is the eyepiece. So you have this object placed in front of the eyepiece. For this setup, this object and eyepiece lens, you want the final image to be at infinity. So, to get the image at infinity, object should be at the focus. That means the eyepiece in this whole setup, the eyepiece should be placed in such a way that this point is also focus of the eyepiece and this distance is equal to focal length of the eyepiece, that is FE. So the distance between the two lenses in normal adjustment, obviously it is going to be FO plus FE. So in normal adjustment, the distance between the two lenses is FO plus FE, that is sum of the focal lengths of the two lenses used in this setup. Now, as this object, that is this intermediate image, say AB, okay, this intermediate image AB is at the focus of the eyepiece, that means the final image will be formed at infinity. So we can draw the final image here in this way. After refraction, the rays will go parallel to each other. So we can denote it like this, that they intersect at infinity. And final image is formed at infinity. So whenever you are using a telescope in normal adjustment, final image is at infinity. The distance between the objective and the eyepiece is equal to FO plus FE. Objective and eyepiece, these two lenses should be arranged coaxially. That is, they should have a common principal axis. So they should be arranged coaxially in such a way that their foci are at a single point between the two lenses. Now, let's look at alpha and beta, because remember, your magnifying power of this device is also given by beta upon alpha. Beta is still the same. It is angle subtended by the final image at the eye of the observer, but there is a change in alpha. So, in case of telescope, because the object is far away from the observer, that is why now alpha is defined as angle subtended by the object at the eye of the observer directly. Okay? Angle subtended by object, distance object at the eye of the observer is directly angle alpha. But then because compared to distance of that object from the observer, this length of the whole telescope is very small. So we can approximately say that alpha is angle subtended by the distant object at the objective lens itself. That angle would also be equal to alpha, at least approximately equal to. So this angle is alpha, then by definition of opposite angles, this angle here would also be alpha. Likewise, just like compound microscope, this angle here is beta, so its opposite angle here, it will be also equal to beta. Now if you take a look at this right angle triangle, for alpha, this angle alpha, opposite side is height of the object, that is AB, and adjacent side is equal to FO, focal length of the objective. Likewise, consider tan beta. So this angle beta we are considering, opposite side, again height of the intermediate image AB, and adjacent side here, adjacent side is equal to FE. So that we have tan beta divided by tan alpha is equal to FO upon FE. Now after this, we apply exactly the same approximation which we have applied in case of a compound microscope, that here angles alpha and beta are very small, and when measured in radians, tan alpha is approximately equal to alpha and tan beta is approximately equal to beta. That implies magnifying power in this case is FO divided by FE. So this formula is for magnifying power of a refracting microscope when it is in a normal adjustment, that is when final image is obtained at infinity. Okay. So another important point, distance between the two lenses is equal to FO plus FE. Again, remember, only when it is in normal adjustment. All right. Okay, that is all for normal adjustment of refracting telescope. Thank you.